then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students, and welcome to lesson number 1 for AP Calculus AB. So just a short disclaimer, this particular video is the first video getting into content. This video has nothing to do about an overview of the course, class expectations, or things of that sort. Videos on those topics can be found elsewhere. This particular video is getting straight into the content for our course. So let's go ahead and begin lesson 1. All right, so here we are. Lesson 1, this is an introduction to limits. I hope you're happy to be here.
Very happy to be here.
Now, some of you have seen limits. Those of you that took pre-calculus with me, you already have seen limits. Those of you that have not had me for pre-calculus may not have seen limits. If you've seen it before, it's going to make this first day a lot more easier for you, which is the reason we cover it in pre-calculus. If you haven't seen this before, it's still going to be explained to a level where you can understand. So just relax and enjoy the ride. So today's objectives, the first thing we're going to talk about is we're going to show limit notation and define what exactly a limit is. And lastly, we're just going to evaluate limits numerically. So we're going to find limits numerically, which basically means we're going to use tables. So we're going to utilize tables to find the value of limits. Now, limit is somewhat of a vague concept, if you will. It's kind of the bridge, in my opinion, from pre-calculus to calculus. And while finding limits, you may wonder, like, what exactly, what are we finding a limit for? What do we even need this operation for? Well, this course is broken up into 3 big ideas, one being limits, the other being derivatives and integrals. So when we find a derivative, it's based on finding the slope of a tangent line, as we'll cover later. And what we do is we take a secant line and turn it into a tangent line, and all that is done from a limiting process. So there's limits used there to pull that off. And even when we're doing integration, so integration is really based off area under a curve, where we find these Riemann sums, where we find these rectangles to estimate the area below a curve. And to really get the real area, where it becomes the actual area, not an estimation, we use an infinite number of rectangles. And to get that infinite number of rectangles, it's really based on finding a limit as n goes to infinity. So limits are the foundation for derivatives and integration. So that's one of the main reasons why we find limits. They also have additional importance in things of continuity and a little more advanced topics in mathematics. But let's look at limit notation, because some of you may have never seen a limit before. So this is how limit notation looks. And I want to read how this is read when you see this. So this is read, the limit as x goes to c of f of x equals L. This is read, the limit as x goes to c of f of x equals L. So in a typical problem, we're trying to find the value of L. Now, it's important to know that L is a finite number, and it's a finite number that the function, in this case f of x, gets arbitrarily close to as x approaches c, another finite number, from the left and from the right. Now, I know that statement, if you've never seen this before, it's not very elucidating. So you may not be able to comprehend the statement right now. And you may not be able to comprehend the statement fully even today. However, I guarantee by the end of tomorrow, what that statement is saying will make clear sense. Some of you will understand it today. Others will need to see additional information. That is when we look at limits from a graphical standpoint tomorrow for it really to make sense. So I understand that right now that statement may not make a lot of sense, but I'm going to try to bring the statement to life. So I want to read the statement again and just understand this is a very technical subject. So every word I use for these definitions is used for a particular reason and cannot be overlooked. So I'm going to read the statement I have written and kind of elaborate on what this statement is saying. So again, we're finding the limit as x goes to c of f of x and it equals L. And it says the limit L is a finite number. So I'm going to stop there for a second. This limit is a finite number, meaning if you don't get a finite number, which of course would be if you were to get infinity or negative infinity, well, that means the limit doesn't exist. Because if the limit exists, the limit is L, and L is a finite number. So sometimes you're going to see situations where the limit does not exist.
If the limit never approaches anything, the limit does not exist. The limit does not exist.
All right, so the limit L is a finite number that f of x gets arbitrarily close to. So you notice I put arbitrarily in quotation. Now, there is a mathematical definition for what we mean by arbitrarily close. It's called the epsilon delta definition. However, if I showed you that definition, I'm not sure it would shed any light on the subject. And that particular definition is not something that's in the AP calculus curriculum. So I'm not going to talk about the epsilon delta definition. However, I am going to loosely define arbitrarily close. I mean, just look at the word arbitrarily. I mean, you're going to get a loose definition. And it just means as f of x gets very close to some particular finite number. And I'm going to show you what I mean through tables, what I mean by very close. So arbitrarily close, as we go through examples and look at tables, you'll get a better understanding of what it means. The best way I can define it right now is just very close. And when you look at the values in the table, you get a better understanding of what I mean by very close. All right, so it's a finite number f of x gets arbitrarily close to as x approaches c. Again, remember, c is another finite number. Well, c need not be a finite number, actually. But for today, c is going to be a finite number. So as x approaches c from the left and from the right. Now, this from the left and from the right business is tremendously important. So if the limit does exist, because again, there's cases where the limit doesn't exist. So if the limit exists, the finite value that f of x approaches, it has to approach that same finite value as x approaches c from the left of c. That means values which are less than c. You have a number line, numbers to the left are less than numbers to the right. So it has to approach the same finite number as x approaches c from the left of c and also from the right of c. So the value that f of x approaches, it should be the same number from the left and from the right. It should be approaching the same exact number. If it does, now that number is the limit. That's simple. Okay, let's look at some examples, shall we? So I have a few examples, and I'm going to find the solution to these problems numerically. All right, so here's number one. So example number one, we're going to find the limit as x goes to 5 of x squared plus x minus 30 over x minus 5. Now to find these limits, I'm going to use a calculator today to do this numerically. Now when you actually do an assignment, you will never need a calculator to find a limit. I'm going to use a calculator today. This is more for demonstrational purposes. I'm going to show you ways to find limits tomorrow and the day after, where you can see how to find limits graphically and analytically, where you don't need a calculator. So for assignments and tests, I will never give you a limit that you need a calculator to find. So albeit I'm using a calculator to demonstrate this, really to demonstrate this today, this is not the method you're going to use when you find limits yourself. If ever on an assignment or a test you find a limit numerically, the table will be given to you. You'll never have to put the function into a calculator to obtain the table. All right, but I do kind of want to explain what goes into plugging this into the calculator to get the limit. So let's go ahead and let's pull up the calculator and let's plug this function in. So there may be times where you just want to check the limit and you might want to do it using a calculator. So I'm going to go through and kind of show you how you do it in a calculator. But again, on assignments and tests, you won't need a calculator to evaluate limits. So what I'm going to do is I'm going to go to y equals. I'm going to type the function in. And the function was x squared plus x minus 30 over x minus 5. Now, so I want to find the limit as x goes to 5. So I'm going to change a couple of things in the calculator. So right here you see in blue, you see table set. So I'm going to change the calculator's table settings because I'm going to look at a table to do this. So since this is in blue, I need to hit second to get to this. So second window or second table set. And this table start that you see here, this is the value where the calculator starts the table. You notice by default it's at 0. So if you were to go to a table, it will start at 0. You know, if I turn this table start to 78 and I went to a table, it's going to start at 78. So that's what table start means. For these problems, you want the table start to be the value that x is going to in the limit. So in this case, we want the table start to be 5. Now you'll also notice this delta table guide. So delta table, again, I want to go back to the table. You notice in math and science, delta means change. So you notice these x values are differing by 1. Now you may also notice these y values are differing by 1 as well. That's just a coincidence. The delta table relates to the change in the x values, not the change in the y values. It just so happens for this particular problem, the y values are changing by 1. On the third day, lesson number 3, you'll understand why that's happening on this particular problem, because we're going to revisit this problem on lesson number 3. But for right now, just trust me and believe me that the delta table refers to the x values. Now, so here the x values are changing by 1. So I want to kind of address this arbitrarily close issue. Again, arbitrarily close means very close. So to be able to get this picture, to make this picture lucid, to bring this into a more high definition visibility, I need this delta table to be smaller. In fact, the smaller the better. I mean, the smaller I can make this, the better. But it comes to a point sometimes you make the value too small. I mean, the calculator doesn't even have enough space to kind of display what you're saying, so it kind of rounds everything, so you really don't give a good understanding of what's going on. So, you know, for instance, I can make this delta table 0.000000000001. That's great because that's a very small value. But if I look at the table, I'm not going to get much from it. So what I found through doing this for so many years is that a good number to use, a good small number, a kind of a sweet spot where it's small enough where we can see what the limit equals, but not too small where it obstructs from the numbers. A good value to use is 0.001. So this will be my delta table for all finite limits. And I say finite limits, that's when x is going to a finite number. Later, we're going to learn about limits where x goes to either infinity or negative infinity. In those cases, you know, I wouldn't choose that option. All right, so what happens is I go to the table. And again, I'm finding the limit as x is going to 5. So this is 5 here. You may notice there's an error on 5. That should make sense. If you look at the original function, 5 would make our denominator 0. And you know when your denominator is 0, the value is undefined. So that's why you see that error there at 5. But I want to stress this point to you. The fact that the function is not defined at x equals 5 has no bearing whatsoever on the limit of the function as x goes to 5. So I want to repeat that. Now I'm going to repeat it in more general terms. Instead of 5, I'm just going to use c. So the value of f of c has no bearing on the limit of f of x as x goes to c. No bearing whatsoever. Now there are cases, in fact there are many cases, and particularly we're dealing with well-behaved functions, where f of c equals the limit of f of x as x goes to c. In fact, that's the definition of being continuous, for the function f of x being continuous at x equals c. But however, when I'm finding a limit, I am not concerned with the value of the function at c, but the value that the function gets arbitrarily close to as x approaches c. So when we're finding limits, we're looking at the values as x approaches c, not the value as x equals c. That's pretty important to understand. So to get that value that x approaches, that f of x approaches, that f of x, gets arbitrarily close to as x approaches c from the left and from the right, I like to put the number that x is going to in the middle. So I'm going to put 5 in the middle here. So there's 5 in the middle, has an error, big deal. And I'm going to look at these values that are less than 5. So this is approaching 5 from the left. So here x is approaching 5 from the left. So it's going to 4.995, 4.996, and 4.997, etc. Getting closer and closer to 5, but less than 5. So approaching 5 from the left. I want to look at the y values. And the y values, as I make this journey to 5, I want to see if they appear to be getting arbitrarily close to a finite number. And I get 10.995, and then 10.996, and then 10.997. And it keeps going. Then I get 10.999. And if you look at that, these numbers are extremely close to 11. So this is what I meant by, I'm going to define what I mean by arbitrarily close by the numbers in the table. This is a prime example of what it looks like to be arbitrarily close to a particular number. Look how close those numbers are to 11. So that's kind of what you want to see when we talk about arbitrarily close. You want to see numbers very close like this to 11. But we only looked at one side. Again, in our definition of the limit, it always says the left and the right. There must be agreement there. So thus far, we've only looked at the left. Let's look at the right. So here are numbers that are greater than 5. So we're going to 5 from the right, from values which are greater than 5. So from 5.005 to 5.004, etc. on to 5. Let's look at the y values and see what they do. And we start off with 11.005, and then we have 11.004, all the way down to 11.001. So I think it's obvious, at least to me it is, that as x approaches 5 from the right, it equaled 11. And remember, as x approached 5 from the left, it equaled 11. So what that means is the limit is 11. So the limit of this guy was 11. So now I'm going to look at several more examples. All of the examples I have plugged in the calculator ahead of time to save some time. There's only one that I'll plug in again in front of you because it's a piecewise function, and I kind of want you to see how we plug piecewise functions into a calculator. But for the others, they've already been plugged into the calculator. I'm just going to make their table appear and see if we can determine what those limits are. Okay, let's look at example number 2. So example number 2, we're going to find a limit as x goes to -2 of 12 over x plus 2. So again, I've already taken the liberty and I already plugged this one into the calculator. So I'm just going to show the table here. And again, when I plugged it into the calculator, I just plugged in the function as you see it. I made my table start at -2, and I kept my delta table 0.001. But anyway, the table looks like this. So there's the table. So let's analyze this table and see if we can figure out what this limit is. So again, you can see I put the -2 in the middle. And here I am approaching -2 from the left. That's from values which are less than -2. And let's look at my y values. So I go from from -2400 to -3000 to -4000 to -6000 to -12,000. So again, we want these numbers to be arbitrarily close to a particular number. Think about the previous example and how close those numbers were to 11. Do these numbers appear to be arbitrarily close or very close to a particular finite number? I hope your answer is no. I mean, just look at it. From -24,000 to -3,000, there's a difference of -6,000, and then you have a difference of -1,000, and then a difference of -2,000, and then a difference of -6,000 as you go from -6,000 to -12,000. So those numbers aren't very close together. In fact, the closer you get to -2, the more spread those numbers are. When you see something like that, and you're going to see this illustrated in the graph tomorrow, but when you see something like that in the table, meaning the closer the values get to your particular number, which in this case is -2, the further apart the numbers spread, that either is an indication of the function increasing or decreasing without bound. If the numbers are negative, as they are on the side we're looking here, we say it decreases without bound, which means that it's going to negative infinity. That's what it means. Decreasing without bound meaning there's nothing stopping you and you're going all the way down to negative infinity. That's what's occurring on the left. But that's enough for us to say the limit doesn't exist, because again, the limit must be a finite number. So if you see any action going to infinity or negative infinity from the left or the right, the limit doesn't exist. So I've seen enough to see that the limit doesn't exist. However, I do want to analyze what's going on the right, just to look at it. So on the right, you basically see the same numbers, but positive instead of negative. So you go from 2,400 to 3,000 to 6,000, from 3,000 to 4,000 to 6,000 to 12,000. So basically the same numbers, but on the positive side. Again, the closer they get to -2, the more spread apart they are. But these numbers are positive, so these values are going to positive infinity. So it's going to negative infinity from the left and positive infinity from the right. So, but since it's not going to a finite number, we say the limit does not exist. So this limit does not exist. So whenever the limit doesn't exist, there's just a short abbreviation that we knew that's recognized around the world, and that is D&E, for does not exist. And so you can write D&E on any assignment, on any test, including the AP exam. So D&E is something that's understood the world over. You can go and find the most remote city in any part of the world. You can show them this limit, and in their language, they're going to say D&E. So everybody understands D&E. All right, let's look at the next example. So next example, here we're finding the limit as x goes to 7 of x squared minus 9x plus 20 over x minus 6. And let's take a look at the table for this particular function. There is the table there. So let's look at what's happening on the left. So here on the left, it looks like these values are very close to 6. And here on the right, it looks like these values are very close to 6. So then the limit is 6. Now, I know you're probably noticing something in this problem that was different from the previous two. And that is the fact that there's no error at this value, meaning the function is defined at 7. But again, I still want to stress the point that when finding limits, we're concerned with the value that f of x gets arbitrarily close to as x approaches c, not necessarily the value at c. So even though in this case, f of 7 was 6 and the limit as x went to 7 was 6, the limit wasn't 6 simply because f of 7 was 6. In fact, there are cases where the value at the point is defined, but is different from the limit. And there's also cases where the value at the function is defined and the limit doesn't even exist. So again, when we're looking at limits, we're not concentrating on the value at the point, but as x approaches the point. In this case, it just so happens that those things agree. But again, we don't want to concentrate on the value at the point. In fact, when finding limits, you can not even pay attention to the value at the point and just look at what happens as you approach the point. But anyway, let's look at the next example. So that limit was 6. So here's the next example. So we're finding the limit as x goes to 1 as an absolute value of x minus 1 over x minus 1. And here is the table of that situation. So here, looking at the left, we get all negative ones. So could we say those numbers are arbitrarily close to a particular number? Absolutely. So these are all arbitrarily close to -1, of course. They all equal -1. And if we look at the right, on the right we see they're all arbitrarily close to +1. So we have -1 on the left and +1 on the right. So what do you think our limit should be? Should we choose 0, the number in the middle? Or should we just say +1, just take the absolute value? No, this limit does not exist. So again, for the limit to exist, it must approach a finite number, which it does here. It approaches a finite number from the left and the right, but that finite number has to be equal. It has to be the same finite number. If there's different finite numbers on the left and the right, the limit does not exist. Okay, let's look at our next example. So this is a piecewise function. And f of x is 5x minus 3 where x is not equal to 2. And f of x is x squared where x is equal to 2. And we're going to find the limit as x goes to 2 of f of x. So this one, instead of just showing the table, I want to show you how you graph this one in the calculator, because many of you may not be familiar with how to graph a piecewise function. And that's something that you may need to do at some point. So let me go to my calculator. Okay, so I'm going to go to y equals. So if ever you need to graph a piecewise function, hit the math button if using the TI-84. And way at the bottom, you'll see piecewise. So I'm going to select piecewise. Now I want to know the number of pieces. So pieces are the number of functions you see. In our example, we just had 2 pieces. So I'm going to say 2 pieces. And notice I used this arrow to make it go down. I could have used this one to make it go up. This one goes down, this one goes up. But again, I want 2 pieces. Move it down to where it's on OK and hit enter. So it puts the 2 pieces in there. Now again, my first piece was 5x minus 3, and that was for when x was not equal to 2. So to get the not equal sign, I'm going to hit second and test. So x was not equal to 2. And the other piece was x squared, and that piece was for where x was equal to 2. So where x was equal to 2. Okay, so there's the function there. Again, I'm finding a limit as x goes to 2, so I'm gonna go second table set. My table start is 2. Again, I'm gonna make this point 0, 0, 1, and let's look at what the table shows. So let's put the 2 in the middle, and let's conduct our analysis. So again, if I look at the left, so here's x approaching 2 from the left, you should say these y values are very close to 7. I think that's obvious. These y values are very close to 7. And here I am approaching 2 from the right, and you should see the closer you get to 2, these y values are very close, again, to 7. Now you may notice here there's no error at 2, but the value at 2 actually is 4, not 7. What do you think our limit should be? Should it be 4? Should it be 7? Or should it be does not exist? The answer is 7. So again, when we're finding limits, we look at the value that f of x is arbitrarily close to as x approaches c from the left and the right. As x approaches 2 from the left, f of x gets close to 7. As x approaches 2 from the right, f of x gets close to 7. So the limit is 7. Again, when finding limits, we are not concerned with the value at the point. The value at the point could very well equal the limit as it did in the previous problem. The value at the point could not equal the limit as it does in this problem. The value at the point could not even be defined and the limit still exists as it did in the previous problem. Or the value at the point could be defined, or the value at the point could be defined and the limit still not exist. So again, if there's any point I can bring home today, when finding limits, we're looking at the value f of x is arbitrarily close to as x approaches c from the left and the right. The value of f of x at c has no bearing on the limit. That concludes our first lesson. I hope you enjoyed it. I did. And we'll see you next time.
Specialize in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.